All right, good afternoon. Thank you, Gideon. So normally, of course, the tradition is that when someone comes to give a speech in this room, that someone introduces them. And I had a conversation that went something like this with Rico. I went up and said, well, Rico, you're the head of all the Impossible Things initiative. Would you like to introduce Bill and I when we talked about Euclidean? He said, you guys talk about Euclidean? No, I'm going to be out of town. And then I probed Rick, because I thought, well, maybe we'll bump up one level of management. And Rick said, no, I think I'm going to be out of town. So no one would introduce us, so here we are. All right. Bill and I are glad. Jeremy would be willingly introduced. So we're glad to be here. This is our last stop on our worldwide Euclidean 2010, Fall to 2010 tour. We've spoken in Cambridge and Silicon Valley and Beijing, and we're really glad to be back to Redmond where there's no jet lag involved in giving this talk. And we're here to talk about, we're here to talk about impossible things, and in particular, the Euclidean impossible thing, which is the third listed impossible thing. And I'll give credit where credit is due. Euclidean is an acronym that Rick came up with. He was in my office one day, we were talking about the project. He came back the next day, he says, oh, I've got a name, and it's even a good acronym. You'll notice there's no N at the end of it. It's the environmental, for user-centric, location-independent data and interactive applications, there's no N. If we're in a pleasant mood, we say now. And if I'm in a mean mood, I say ninny. Okay? All right. So I want to talk a little bit about impossible things before we go any farther in. When Rick and Rico started talking about impossible things, I got quite excited. It seemed like a great thing for MSR to do, but I was trying to get my head around what exactly it meant, what were the impossible things. And so here's my model, my description of what it means for us to build impossible things. And that is that we go off and select some impossibly ambitious target scenarios that spans fields in which we have expertise within MSR. We go and build a new artifact by taking artifacts that we already have, technologies, code, ideas, etc., pulling them together and adding new work as needed to start out with to get an initial artifact, and then start evolving it, evaluating the artifact in progress against the target scenarios, and rebuild and reevaluate. Okay, and I think one of the key things about these impossible things is that there is an artifact, there is a thing, and that becomes a vehicle that allows collaboration. And I'll come back to that a little later. Actually, a couple of times I'll come back to that. The other question one might ask is, why should MSR build impossible things? And my short answer is to live up to our potential. I think we have more talent and better institutional support at MSR for doing large projects than at any other institution in the world, any other institution on the planet, and that we should take advantage of that. And in fact, I'll go as far as to say we have a debt to humanity because we've been given this opportunity that we should fulfill it. So that's why I think we should do impossible things. And what should you do about this? Well, I'm going to give you a Euclidean context to this, but I think everyone should look at the other impossible things as well as appropriate. As I go through and talk today, I want you to be doing four things. One of them, actively looking for opportunities of, do you have code or algorithms that you've invented in your research that we should be employing in Singularity? And let us know about those. Second one, all right. Yeah, I've done this before, haven't I? It's called, in Euclidean, I'll try not to say that, and I'll try not to say Menlo today as well. Okay, I will say Euclidean. The other one is, do you have ideas that we should be using in Euclidean? And then finally, third one, can Euclidean give your research better context? So if you do your research in the context of Euclidean, might it give better research context? Might it give better examples that you can use, better demos, things like that? And finally, should we, when we talk about we starting out with Bill and I and then expanding rapidly out, should we include you? Okay. And so those are the four questions I want you to keep in your mind. The other thing I'm going to do is a bit of a disclaimer. Bill and I are systems guys. I apologize. Anything above ring 0 I call application. So some of the terminologies and some of the things we're going to say will come off as a bit system-centric. The intention is that Euclidean is not just a systems project. I think it spans everything from human-computer interaction to generically applications, to hardware, to just about anything that anybody here in MSR is doing, I think could be served by operating within the context of Euclidean. Okay, so leave that out there broadly. All right. So what are we trying to do with Euclidean? Well, what we want to do is fundamentally change the way that humans interact with computation. And we want to build a system and build an experience and applications that have three unique qualities beyond what any other system has ever had before. The first one is physical awareness. And this is that the computation actually begins to understand the physical world outside of the box. Okay? It understands that there's humans. It understands that there's a physical world. It understands what the orientation of the physical world is and is able to participate in that physical world with us. The second one is device aggregation. And this is that user experiences can span multiple devices simultaneously. Okay? The third one is what, for lack of a better term, I call follow-me computing. And this is the idea that applications shouldn't be bound to a specific machine, but they can reach out to humans wherever they are. Okay, and they can follow the humans as needed from device to device so that they can maintain proper interaction ratios, say, within 5 milliseconds for interactive interaction, et cetera. Okay? Now, to give a little more body to these descriptions, one of the things we did very early on in the project, and we've been toying around with some of these ideas for, I don't know, about 4 to 6 months maybe, is I went through the Office Labs group has created a series of videos. They call them the Industry Innovations videos for what computing might look like in 2020. And it's total science fiction. Okay? They actually went around and asked researchers, hey, what might you imagine somebody doing even if we had no idea how it might be done? And we went and took the videos. I took the videos and analyzed them frame by frame and said, okay, if we're going to make this possible, what would a system have to have? What features would a system have to have in order to make this vision possible? What would we actually have to build to make this real? And so I'm going to just show you a collage of these. Okay, so first we start out with two business partners that are collaborating through three devices very easily. And they're not in slow motion, it's just my video that's in slow motion. Okay, we've got a man whose coffee cup and his other devices help him get his workday started. Okay, so the coffee cup realizes he's drank enough coffee. We can now pull up his agenda for the day. Let him pick up work from one display, move it with just some gestures over onto another display. Man comes into a bank interested in an auto loan. Okay, and he uses both wall displays and his tablet. Another customer exchanges financial data with just a physical gesture. Okay. Patient is helped to take his medicine with the bedside display and the nightstand. Doctor gives a cornea exam with a camera, the bedside display, and his slate. Now the doctor's going to join a patient confidential video call, and the room facilitates that, including obscuring the glass so the confidentiality is maintained. finally, a dead battery doesn't mean a loss of service, it just means a change of device. Okay. So, all right, so you ask yourself, well, why is this vision hard to achieve with the systems that we have right now? There's three primary reasons. The first one is because our systems lack any environmental awareness. They have no idea of what's happening in the physical environment around them. Okay? And so instead, users have to tell them what's happening in the environment. Second one is that our abstractions that we provide in operating systems for accessing devices, et cetera, are very device-centric. For example, if you think about what does it take to display this slide on this screen, well, I have to tell my PowerPoint which display is the right one to use, for example, okay? And I have to navigate, say if this display was connected to a PC, I'd have to RDP to the appropriate IP address to get to that machine, et cetera, right? Imagine instead that the abstractions were more human-centric, and you could ask questions like, which display is visible to Galen and the 30 people he's talking to right now, for example, okay? And be able to do things like that. And finally, the other problem with our current systems is that our current systems know about users, but they don't know anything about humans, okay? And there's no match between them. The only thing that makes you the only thing that matches you as a user or you as a human as a user in most of our systems is you happen to know the password, and that's it. Okay. And so going through these videos, I'm going to start. There's 4 features that you would want in a system in order to be able to achieve this vision that we've set out for Euclidean. So the first one is this idea of environmental awareness. Simple things such as which wall display is Brad currently holding his tablet closest to, for example. Another one is human-centric ideas of security and policy, particularly human-centric models of attention, prioritization, and confidentiality. Third one is this device aggregation. So this is the ability to take multiple devices and pull them together into a single user experience seamlessly. And then the other hard problem is this idea of the reuse of non-precious devices. And so state should be precious, but a particular physical device should not be. And we saw this in the example of the slate where the battery's done and he throws it up on the wall. Other examples that come up in the video there's these wall displays quite often, or the bedside display. These devices that can be used by multiple users for multiple user applications. And maybe it's prioritized based on who's in the room. For example, the doctor comes in the room, he gets prioritization for the bedside display, but it then goes back to being the video that the patient is displaying. Okay, and so let's see. I'm going to pause right here. So I hope I've accomplished one goal so far. Okay, and that is I hope you've at least got a sense of that this is an impossibly ambitious target. Okay. I hope I've convinced you this is a hard problem to go about achieving, okay? I'm getting some nods of heads. Some of the tough guys in the room, Jim Laris is shaking his head back and forth. He says, no, piece of cake. All right. So with Euclidean, what we want to do, we want to build a new model of computing, grounded in the physical world. We want to build new applications, new experiences, and a new operating system, and particularly new abstractions in the operating system. And Bill and I both share the same advisor at University of Rochester, Michael Scott. And one of the things that Michael taught Bill, he tried to teach me and I wouldn't listen, I think is what happened, is that as an OS designer, we're abstraction merchants. Our job is to build abstractions that make it easier for other people to build programs. And so we think we need new abstractions that allow first to bring in a physical model of humans and devices into the operating system, provide a more user-centric I/O model, and provide security and naming that are grounded in the physical world. Okay, and these are going to require new abstractions, or at least new packaging abstractions. So you might be asking a couple of questions. All right, so if we're proposing this Euclidean impossible thing, well, why should we do this at MSR? Why not someplace else, for example? And my first answer to that question is Microsoft has unique expertise and also artifacts that we can do this with. And we've got things like we've done Natal, Surface, Vision. Got work out of the adaptive systems group. We've done a lot of work in sensors. There's some distributed systems artifacts such as symbiosis and other operating systems artifacts like Drawbridge, where these are technologies that I think would allow us to pull, if we pulled them together, we could actually go quite a ways to achieving this vision right off. Okay, and insert your research here. there's roughly 50 people in the room, 50 pieces of research. I think there's many other things that might be brought in. The second question, why MSR, is, well, we've done this sort of thing. An example I hold up is singularity. So in the case of singularity, we built an operating system completely from the ground up in managed code with the purpose that we were going to apply as much static analysis as possible pervasively in the system, more so than in any previous system. And one of the core ideas was that the code base of the operating system itself would become a laboratory and a point of contact for diverse groups to do research in. And I think by any metric that you want to evaluate the success of a large project, I think singularity matches that metric. So in terms of collaboration, where we had 30+ researchers over a number of years, we had 3 labs, we had areas ranging from operating systems to tools, languages, and security. In tech transfer, we had a number of ideas that went in both into core products, but also there's the Midori incubation that's off running with on the order of about 80 people that's taken our code base and gone from there to scholarship. Over 25 papers and patents came out of it. So I think by any major, and my assertion is that we, as a company and as an organization, we have some idea of how to do these kind of large projects and be successful at them and make them successful for the individuals that are in the projects as well. So our status with Euclidean right now is, as I mentioned, a couple of us have been thinking about this for a number of months. Over the last 2 months, maybe 3, there's been a group of about 8 of us here, primarily in MSR, working on building a seed of a system. Okay, and the way you should think about what we've built so far is we've built just enough of a system to have an artifact that people can come and collaborate around. Okay, and we'll talk about architecture and some things, but the way you should think about the architecture of Euclidean right now is it's in pencil. Okay, we know that pieces are going to have to be replaced. We know that it's going to evolve, and we're here today looking for people who want to collaborate and get involved in that. Okay, and I will turn over to Bill to talk about where we are really.
Okay, so the first thing to note about this picture is that there's a rock up on it. Remember how, if you listen to Rick give the Impossible Things pitch, he said that the model should be stone soup? Well, this is just a stone, right? This is just enough in the thing to give you some idea that we can do this, and very little of the code that we have will probably survive to the end. So we wanted to build a demo that showed some of the things that we think Euclidean systems will need. So we built a demo that is a bouncing ball. So the ball, I'll show you in a minute, bounces from bounces around on a slate, and it's aware of the physical gravity. So when you turn the slate, it bounces towards the bottom of the slate. And it's also aware of the proximity between devices. So you can take the slate, you take it over, and if you dump the ball out, there's a little hole in the frame. If you dump it out the side, it'll fall into the nearest slate. So you can do that, and it's aggregating devices. There's a single application that's running on, actually running on my laptop, that aggregates 4 devices. The laptop itself where the computation runs, and then 3 slates, one here, one there, one over there. So to the application programmer, which was mostly me, it looks like it looks like just a single world with windows and sensors and things. So you don't have to deal with writing a distributed application, which we thought was kind of a nice thing. And the idea was that we would build enough of the system so that an intern could modify the single machine bouncing ball application to run on Euclidean in a day. And we achieved that goal if you're willing to define intern as principal researcher and 1 day is 2 days. So pretty close. Close enough for research anyway. Okay, so.
Yeah, we have to have a third person here.
Okay, so.
All right, right here, Gideon.
These things are very old slate devices. The terribly old hardware, but this is the ball. It would bounce, except it's just sitting on the bottom. This thing is a sensor package that Jeremy Elson designed and had fabbed, and it does a couple of things. One is that it's got an accelerometer that's used to measure gravity, and so you see the ball is bouncing down, and we have some little communication bandwidth problems that Turns out they're related to named pipes, but we just found that out this morning. So that's why it's kind of laggy and jumpy like that. But the point is, when you turn the slate, eventually the ball falls in the direction that's physically down. So it's aware of the orientation of this thing, unlike if you had just written, well, when I wrote the application without the eel. The other thing that happens is that these things are ultrasound transducers, and it uses ultrasound chirping to tell the distance. Okay. Oh, did it?
Is broken.
His gravity's broken. Hold it the right way.
Uh-oh.
Hold it. Is this an iPhone?
Is it still running here? Did you bump the sensor? Well, I don't know. We'll see in a minute. It may be that your gravity's broken and the demo may end sooner than planned. But we also discovered that USB ports are actually a little futzy. So the idea is, it's got an ultrasound transducer, and it sends out chirps, and it can measure the distance between these. So it doesn't really have a 3D model of the world. It doesn't actually know that this is higher than that one. All it can tell is that I'm 3 meters from Gideon and 7 from Galen is all it can tell. And we'd like to have a better model, but with the sensors that we have, that's all we've got. So we're going to try this, but it's a little frightening since gravity seems to have stopped on Gideon's. But I'm going to turn the thing. Okay. It's also got some pipeline lag in it, but the ball will fall out the corner.
Oh, it's right.
Oh, it went to Galen. Okay, his probably just.
Gideon has died.
Gideon's died. So what happened is his hardware died, and so it couldn't find it, and so the closest one was over there.
Yeah.
So you can bring it and pass it back to me. There, and it came back here because it.
There's 2 of them.
Oh no, that's just pipeline lag. There's really the program thinks there's only one, but the name pipe bandwidth to these things is so terrible that the frames that are getting sent over there take longer to render than the smaller frames that don't have the ball in it. So there's really only one. You just thought you saw 2. Yeah.
How does it figure out which way is down?
Oh, it's got an accelerometer.
It's like a cell phone.
There's a piece of in that piece of hardware that Jeremy built. There's an accelerometer, and basic physics says you can't tell the difference between acceleration and gravity. So as long as we're not accelerating the things, the acceleration vector always points down
By 1G.
by 1g. And in fact, one of the very first things, as soon as we got it, we plugged it in with just the version with the little arrow on it and spun around like this to create an acceleration, and the arrow moves. And right. So I got paid to spin around in circles in the hall, which was kind of fun. Okay. Okay. So what's really in this system? So we've got the very primitive location service that I told you about that works by using just the ultrasound probing. And we need more sophisticated sensors to do better 3D models. We've got drivers for a few devices, meaning the EEL, the sensor board that you saw, and something that offers remote display capability, and something that allows you to run a computation, and a random number generator, I think, that we used for testing. That one wasn't in the demo. A non-dimensional model of the universe. What that means is pairwise distances, but it sounds better when you call it a non-dimensional model of the universe. And then we took Euclidean, and we ran it in this thing called Drawbridge that Galen mentioned very briefly before, and he's going to give you a demo of later. But it's a, yeah.
If you have enough such devices, then distance is enough to make a pretty good dimensional model.
It is, actually, but we don't. We only have 3.
2 of them, no.
Yeah, we only, well, yeah, once you got a hold of it, we only had 2. So,
Made the method.
okay, so Drawbridge allows you to encapsulate Win32 and do security stuff with it, and also to change it. And what we did inside Drawbridge was modify the Windows abstraction a little bit so that you can say add a device, add a display to you. So to the Windows application, it looks like that's running on a laptop, it looks like it's got a triple wide display, and it just put up 3 windows, and it happened to know that one piece of it was here, one was there, and one was there. So it has no awareness of humans, even to the extent that there's not even a type defined for humans in the version of the code that's there. It hasn't done 3D modeling, and we probably won't do it with ultrasound. We'll probably use Kinect sensors because they give you 3D models a lot more. They give you depth, and you can synthesize it out of that. And some people in Cambridge have done some wonderful work with that we can import. we don't have any persistent state at all. We don't have, I mean, lots of pieces of the system are there. We just cobbled together enough to get the ball to bounce. And we're going to add all the rest of it as need be, or maybe you will help us add it. So how did the code work? There's essentially 4 different things that run on the system. There's the cell server, where cell means cell is in cell phone. So it's a piece of infrastructure that it'll run on one computer somewhere in a building. Just think of building size cell, and it keeps track of sort of who's in the building and roughly where they are and who's got what sorts of devices. So you can use it for queries to find out the basic shape of things that you can then talk directly between the things to do things like move sensor data around. There's a host server that runs on every machine, and there are 4 machines, right? This one's my laptop, and then the 3 slates. And its job is to interact with the devices that are on there, interact with the cell server, interact with any applications. It's kind of the glue that holds everything together. There's some drivers. So EEL is the alternately Euclidean or Elson experimental locator. And so it's a driver that reads the COM port and understands the little things and turns it into gravity and proximity. There's an RDP client. RDP is remote display protocol. That's how we actually put the windows up, is running RDP across the devices. And then the last piece of software is the application, which is almost like a normal Win32 application, except a little bit of this Euclidean code that I mean, it took me a week or so to write the application and about 2 days to make it run with Euclidean. And it might have taken 1 day, except that some of the pieces of Euclidean that I needed weren't written on the first day. So it's that, I mean, we're at that stage of the project. So here's an example of what it looks like. This is a piece of the initialization code out of the system. So it starts up, it attaches to Euclidean, it says, tell me all of the, and the application is running on here, it says, tell me all of the machines in my neighborhood that have a display function. So there are 4 total machines, but only 3 of them have the display function. This one won't do remote display. So the Euclidean comes back, it goes up to the cell server. The cell server says, well, there's 3, and here they are. And then for each of them, it grabs that display, and it says, add to running application, which extends your desktop to go over them. This is probably not the API that we want in the long run, but it was the one that was straightforward to do with Drawbridge, so we built it that way. Later, I think it would be much better to say, create window on display, but that's not, we'll have to modify Win32 to do that. And then, when it looks at display, it goes up and it says, well, find me the accelerometer that is attached to that display. If it's got one, then remember it. Okay, so this is just a simple piece of initialization code that points out that this thing isn't a distributed application. It's much easier to program than that. We didn't even do, if you were to attach a new display once the app started, it wouldn't find them. This is something you clearly would want to put in the system, but we didn't even build that because we didn't need it for this demo. Okay, and the last thing, this is a picture of, I should pull out the one that Galen played with. There's a picture of this board that Jeremy designed and built. And it's got a bunch of sensors on it. We only used 2 of the sensors. We only used the accelerometer and these things. It's also got a gyroscope and an altimeter and a compass and all kinds of good things that we can use to do more awareness once we finally find a use for them. But one of the things that this shows is that we're able to do hardware fab on a pretty short time frame, and it really didn't take very long to design this thing and then send it out to, was it Michigan, Jeremy? Someplace. Colorado. Okay, somewhere in the middle of the country. Send it out to somewhere in the middle of the country, and for a small number of thousands of dollars, you get a handful of these things back in a week or 10 days, which is actually a pretty amazing capability when you think about it, right? It's all surface mount. It's nicely done. This is the second rev. We've got another one coming. Yeah?
Did you get the piece of hardware right the first time?
This is rev B. And if you look really carefully, there's a resistor soldered on the back of it. But pretty close, actually. It took 2 revs and a resistor, so that's not too bad. One of the things that we learned is that it actually works better if you put the transducers on both sides of the board, because the ultrasound is very directional. And this demo worked because the ultrasound was bouncing off the wall. If you do it in a big open space, it might not have worked. And I think, yeah, Gideon.
Method enough to stop the display being stolen by the technicians across the wall in the next room.
To stop what from being stolen?
That is, radio communication works across plywood walls. So is the fact that you use ultrasound enough to stop the technicians in the next room from suddenly grabbing the display?
Oh, well, the display is traveling over just plain old 802.11. All the ultrasound is.
It goes through walls.
It's just plain Wi-Fi for the display. The ultrasound does not go through walls, but we're not sending signal on it. All we're doing is just chirping.
Enough to stop the display disappearing from this room and going into the technician's room.
Yeah, it is. Okay. It is. I mean, it won't detect the ultrasound. If we had another, I think I understand your question now. If we had another one of the slates on the other side of the wall, would the ball go in there? And the answer is no, it wouldn't, because it wouldn't hear it, because the ultrasound doesn't go through walls. But the actual bits were going over the wireless network. And
why can't you use this Wi-Fi network instead of the ultrasound? Why do you have to use ultrasound?
Oh, is that you mean why don't we do proximity with Wi-Fi?
Yeah, I mean, I actually don't understand technology.
So there's been some work done on doing proximity with Wi-Fi, and it's tricky to do at the kind of ranges that we're looking at. The way the ultrasound works, the speed of sound is really quite slow compared to computers. So the way that the ultrasound ranging works is it sends out a chirp, and it picks one to send out the chirp. The other two listen. Actually, it just does pairwise. So it sends out a chirp. One of them listens. When the listener hears the chirp, it chirps back, and then the receiver listens for that second chirp, and then it can tell that it looks at the time from when it sent the first one to when it got the second one, and that time is big enough that you can measure it with regular computer clocks, right? If you did that with, if you did it with RF, the propagation time there is hundreds of nanoseconds, and it's
a few nanoseconds.
Sorry, you're right. I'm off, but it's 10 nanoseconds. I missed by an order of magnitude. So it's like 10 nanoseconds, and you can't, and that's completely overwhelmed by the radio stack, so you couldn't measure distance that way. You could also, people have done distance measurement using Wi-Fi with signal strength, but that's sort of fraught with peril. So we decided to try ultrasound. Ultrasound has got its difficulties too. We're not wedded to it, but it was a piece of technology that we could build pretty easily and try, and it's served its purpose so far. More questions, or I'm giving back to Galen? Okay.
Yeah. I think one of the things to point out about the hardware is, we intend the project not to be wed to any single physical sensing technology. In fact, see it as an opportunity to explore quite a few of them and bring in quite a bit of sensing research that way as well. All right, so we said we were going to build a new operating system for Euclidean. And in fact, we're not actually going to build a completely new operating system. Jim and I have done that once before. We're not in a big hurry to do it again. And so what our strategy, in fact, is going to be is to reuse as much of Windows as we possibly can, but dramatically refactor it for this new purpose, to build a new distributed system that is device independent out of it. And to give you an idea of the scope of both kind of what I mean when I say radically refactor, and also what I mean by I talk about, we're going to be very careful and not modify everything. I'm going to talk about this drawbridge system, which is one of the pieces we use in Euclidean right now. So drawbridge is a technology we developed in my group that provides a private sandbox subset of Windows for hosting applications. And basically what we do is we create what's called a pico process, John Hall's term, where we have a single process, and inside that process we run an application and its own private copy of the Win32 subsystem, which is the portion of Windows that provides the rich application environment, and also an RDP server. And they all run inside of a single process, and then they can communicate out to the world, say out to RDP clients through pipes. And what this technology enables is three things. So it enables secure isolation. So we can make sure that app can't get to any piece of the host operating system outside of its Pico process. It provides legacy compatibility. So inside the bubble, we can run whatever version of Windows the app wants to have. So it can run Windows 7 or Windows 8, independent of what the host operating system is running. And it also enables migration. So we can suspend a process, a Pico process running on one machine, pick it up and move it to another machine and resume it again, independent of the rest of the operating system. And we can do this for a fraction of the cost of a virtual machine like Virtual PC or Hyper-V. Okay, and so to ground this a little bit, so if you look at the way Excel runs on traditional Windows, it's got some DLLs that come out of the system, user32, GDI, kernel32, that provide access to system services, and then there's the main piece of the services comes out of this thing called Win32K, the Win32 subsystem running down in the kernel. And then it leverages the rest of there's really, if you think about Windows, there's really two operating systems. There's NT, and the device drivers that abstract hardware. And then there's a Win32 subsystem that provides services to applications based on that abstract hardware. And what we've done with Drawbridge is we actually take the Win32 subsystem. There we go. Okay, so we take the Win32 subsystem, create a new copy that is in the Pico process with the RDP server, and then we isolate that process. We actually remove access to all of the normal system calls that process might have access to normally. Okay, and instead it gets a very small API set. It's about 32 system calls instead of 1,200 that a traditional Windows process has, that come down through the security monitor, the DKmon, and that can vet and decide what security policy we want to provide access to. Okay, and that provides our component. So I want to demonstrate the system really quick. We actually showed Drawbridge back in, let me minimize this, back in March at TechFest. And at that point, what we basically had was we had Reversi running. Okay, now I've just run Reversi. You're going to notice a couple of things immediately. You see no UI. That's because it can't talk to the Win32 subsystem running on my laptop. Okay, it's got its own private Win32 subsystem, and you can actually see the private Win32 subsystem right here. It's a separate DLL that gets loaded. The other thing you'll notice is that none of these files are coming out of Windows System 32, which is where they would normally come on a Windows box, but instead they're coming out of private per application directory. Okay, and it gets its own copy of user 32 and GDI 32. Here's the RDP components for the RDP server. Okay, and then the application is right there as well. Okay, so it's running inside its completely isolated container. Now I can connect an RDP client to it, and I can interact with it. And you'll also notice it's really a Windows 3.1 application. It's running in 32-bit mode, but it really is a Win31 application. Now, one thing to mention about RDP. RDP is a stateless protocol. Stateless in the sense of I can disconnect the client, connect a new client, and I get my state back, because the state's actually in the Pico process in the RDP server. It's not in the protocol per se. Okay. Likewise, the protocol between the app and the kernel that goes through this security monitor is stateless as well. And that's why I can disconnect a Pico process from a kernel, move it to another machine, and reconnect it to that machine's kernel. Okay. So that's where we were back in March at TechFest. And we've since done quite a bit of work to bring in more sophisticated applications like Excel. Okay. And this is Excel 2010. And it's actually running. You can interact with it, etc. Okay, and you'll notice that we had to bring in a whole bunch of components to make this work. We have OLE32 and RPC and user themes. It's a modern application, for example. Yes.
Did you have to add any additional system calls to make that happen?
So the question is, do we have to add any additional systems calls? I will say this. So from March until May, when Excel started running, we went from 27 system calls to 32 system calls. And the primary thing that changed is we reworked the way that we did synchronization of threads and exposed a little better API. Yes?
What about network applications? You're saying like the state is in the Pico process, not in the kernel, but like TCP, IP, the socket information, it's kind of stays in the kernel.
Yeah, well, we haven't decided how to do networking yet, okay? That's the short answer to that one. We've got about 3 different proposals, and we haven't quite decided, okay? All right, anyway, so there you see Excel running in Drawbridge. We've gone ahead, after we got Excel running, we've brought in, I did do the experiment to see where we kind of reaching closure in terms of the number of APIs that we had. So I brought in PowerPoint. PowerPoint took 2 days to bring in after we had Excel. And to give you an idea of the complexity, so we did have to actually make some modifications to the applications. In the case of Reversi, we didn't have to make any. Now, we modified Excel and PowerPoint, and what we had to do with them is we had to disable licensing. Okay, so we had to disable the copy protection. And that's because it was easier to disable it than go reproduce all the infrastructure for copy protection. There's a question about what the right thing to do. And in fact, this version will run on a regular Windows desktop, so I'm very careful that binary doesn't get very far other than on my machines. Okay. The other thing, another couple of things to note. So most of the changes we made actually went into Win32K. But we added or modified basically 6,000 lines of Win32K. All right. And really we modified about 1,000 lines and added about 5,000 in Win32K. And that's to take Win32K, move it up out of the kernel into user mode. Those of you who've been around a really long time will remember it once was there before. And also to remove the security out of it, or disable it. Basically, Win32K on a traditional Windows system knows about multiple sessions and multiple users and asks questions like, is this a privileged process, and things like that. Our policy here is we always return true. Okay? And that's because the security for Drawbridge happens outside at the container. It doesn't happen inside Win32 anymore. So a couple things that I want you to take away from this, let's see, I might even have this, nope, not yet, is that, yes, we had to modify some big pieces of Windows, but it turns out we didn't have to modify very many pieces of Windows. But what we end up with is our own private version of the entire Win32 Windows subsystem that we can run on Windows 7 machines or Windows 8 machines or anything else. And so we can produce a version of Windows that, from the application environment, that is customized for Euclidean applications. So when Bill talks about, well, we really want to modify the create window API so it takes an argument that says which display you want the window to show up on. Well, we can actually do that in a very backward compatible way. Yes, Alec.
So I understand that Drawbridge existed before Euclidean, but did you consider .NET at any point in time for your app model for Euclidean, or were you inherently wedded?
Yeah, so the question is, did we consider .NET as an alternative app model? We did, and we actually use it as well. So for example, all the device drivers in Euclidean are .NET, and we use app domains and have an environment that basically we can do app codes that way. One way, I will say this, one of the things in doing a large collaborative process like the project like this, one of the important things to decide is what you're not going to do. And initially we decided we were not going to do distributed applications. Okay? So the system is distributed, but the individual applications run on a single machine at any one time. Now, if some very clever researcher at Microsoft says, hey, I've got a great way to do distributed applications, we'd love to have you come participate. That person come and participate in Euclidean. It's just, right now this is what we've done. Okay? But anyway, so we got our own private version. So we got this very low friction path forward from Windows into Euclidean. Out of Drawbridge, we also get this idea of the follow me migration, so we can pick up a process and trivially move it from one machine to another. And it also, because of the RDP, and we've actually been able to refactor the way RDP works, and that gives us a very good story for basic user HCI devices, so displays, keyboard, and mice, for example, for how we can have an application that spans multiple of those. Okay. Now, across all Euclidean, we've answered a few questions in pencil, as I describe it, and there's many other open questions. Okay, and there's actually, we have a design note that lists like all the ones we could think of, and there's too many to actually make them readable. But things, for example, of, well, if you had an operating system like this, how would you allow multiple users to collaborate? What does the user experience look like when you have multiple users collaborating in a physical space, for example? Okay, or given that we've got sensors and we've got an operating system that understands that humans exist, how do we figure out where the humans are and what they're doing and do it in a secure way? And how do we maintain privacy around that information, for example? So there's many other questions that you might think of. And again, insert your research here. Now, so the question, all right, so the big question, how do you participate? Okay, because that's what we're here. We're trying to convince people that you should come participate in Euclidean. Well, what we're going to do is, in some sense, learn from the lessons of doing Singularity and Menlo and some of the other large projects that have happened here, in that we're going to do a collaboration organized around the idea of researchers with cooperating but independent research agendas. Okay? So you should focus on what's your research agenda, what's the thing you want to achieve, and then ask the question of how could Euclidean provide context for that and enable you to better leverage the resources of the people around you as well. Gideon, did I see a hand go up? No. Okay. The other thing is that we have this idea of a shared code artifact. All right. And so you get the benefit of other people are building pieces of the system that could be useful to your research, and so you get that by coming in the environment. You also get the benefit of when you get done with a piece of research, rather than publish the paper and archive the work and that's the end of it, actually being able to put that code back into a code base where other people can immediately benefit out of it. And I think that's one of the greatest benefits we saw, particularly like in Singularity, for example. Chris Hoblitzel is still using pieces of Singularity for his research that he's been doing, years after the rest of us all moved on, for example. Okay, and the other thing, one of the other questions people ask is, well, if you've got a lot of people and you're coordinating, how do you do decision making? Okay, and basically there's a process we kind of developed with Singularity we call the design note process, and the idea is that we organized the thinking about decisions and particularly the decisions that affect multiple people across the project in 4 levels. First, in terms of principles, then architecture, implementation, and user documentation and usage. And we document the decisions at each level that we need to, and we only go as deep for any particular subject as we need to. And finally, we do have the model of a benevolent despot. That would be yours truly and Bill. Okay. And that is that there is somebody ultimately at the end of the day that has to call consensus. Okay. And so we move people toward making as many consensus decisions by as much unanimous consensus as we can, but where there can't be, well, we just call a decision and move forward so that the project can be moved forward. But using the design notes as a way to document why decisions are made and what went into that as well. Okay, so call to action: get involved. We hope you'll get involved, and what you can do. Well, ask questions. We have the DL that's for the group. It's the Euclidi. Okay. Or talk to Bill and I, or talk to the other people in the group. Read the OneNote. We've pretty much captured all of our thinking so far, the analysis of the videos. Everything else is in the OneNote, so you can go read it. Also, our design notes are there. And you can check out the current artifact. Design Note 1 actually tells you how to enlist, build, and run Euclidian, the artifact that exists so far. So you can try it out and figure out truth in advertising, figure out what's really there and what's not, and think about how you would contribute your pieces to the system. And finally, join the discussion. We have Thursday afternoons. We meet upstairs and have design discussions, largely around these design notes. And then we also will do some biweekly status meetings as a way to keep the momentum going and to help people coordinate very actively. Okay, so we hope you'll get involved, and that's all we got to say. Questions? Bill, come up. Yes.
Can your Pico process run DirectX apps yet?
No. So the question is, can we run DirectX yet on the Pico process? And no, we don't. No, we can't. And I'm hoping we've got some smart people that will figure out how to do that. Because clearly you'd want to do it for a lot of things. Get in.
There's a nitpicking, but have you had a retinal scan done recently?
No.
It's a piece of artillery.
Yes.
Okay.
Well, see, sensors are part of the project too.
Yes.
Anything else?
All right.
Okay, thanks for coming.
Thank you.